Who wouldn't want to be more time efficient? Who wouldn't want to have a more stable system and have less bugs or less downtime in production? I claim that if you will understand and utilize parallel testing in your system, then you can enjoy those benefits. Our main goal today will be to use already existing parallelism features in our testing frameworks to reduce the time it takes for us to execute our testing suite. And that is going to save us a lot of time because we run tests all the time. They are everywhere. We usually start our development cycle when we change, modify, or add business logic to our code. Then we usually also run existing tests. Then we also add new tests or add new logic to them, so we run them again. Let's not forget, when we commit and push our code, we will run our tests once more. Afterwards, when we deploy our code to a staging environment, and then also to production, then now our tests are going to run on a different machine, and that is still going to consume us some more time. So even if we save a small fraction of time here, if we multiply it by these times that we run our tests in their development cycle, then it's going to have a very big impact. And also, let's not forget, we run our tests when we deploy to production. So if, for example, you have bugs or have downtime, so now your hotfix can be deployed even faster. So to get a sense of the numbers or how much time you can actually save here, this is just some example project I took for my job at Lucia. All I did was just incorporate some very basic configuration there, and I've managed to boil down the time it took for me to execute my testing suite from 44 seconds to just 20 seconds, which, well, it's even less than half of the time that it used to take when I started out. And it took me around 2 minutes to just make this happen. Now, if parallel testing is as good as I say it is, and it gives you so good results, then why is it not the default behavior in all of our testing frameworks, and we just use it all the time? So to find out, you'd have to stick around. But before that, let's talk about me. My name is Jordan, and I've been a full-stack developer for the past 6 years. And in this time, I write code every day. And I'm also a believer in testing, so I write tests for my own code every day. Today, I work in Lucia. By the way, we're hiring. I'm a full-stack developer in the R&D core team, and my job is to take our already outstanding developers and make them even more efficient at what they do. Now, I've said the word parallelism a lot, and I'm going to keep saying it over and over again. But what do I actually mean by that? So we would actually see two definitions here. The first one is concurrency. And when I say that, I mean that we would have several tasks, and then we would run them in a somewhat overlapping time periods. But it doesn't necessarily mean that we are running them at the same time. So a good example for that is a single core CPU that can make really fast context switches and give you the illusion that things are running simultaneously, when in reality, they just don't. And so we also have parallelism. Now here, for every given point in time, all of our tasks are actually running, and the performance benefit we're going to see is actually going to come from that. So to implement parallelism in software and computing in general, we usually tend to go to two approaches. The first one, we have multiprocessing, where each process would handle a single test file at a time. And then we also have multi-threading. Now, since every process only handles a single test file, this can only help us in the scope of a single test file. Now, I want to start seeing how does our testing frameworks works behind the scene, and also how do they implement multiprocessing, because later it would help us to make some very good optimizations when we later configure our testing framework. So when we start up our framework, the first thing that it will do is that it's going to scan your file system looking for these test files, and it's usually going to do that using some regex provided by the user, for looking for all sorts of patterns, maybe files in a directory. Now, for every file that it finds, it's going to insert it inside a priority queue, And after it's done, it's going to spawn new workers to actually run those tests. So what's a worker? Well, actually, when we started out our testing framework, we've created a new process. We're going to refer to that as the master process or the main process. And those workers are actually sub-processes belonging to this main process. Now, the way it works is like this. Whenever a worker is available, it's going to receive a new file from the priority queue. Then it's going to execute the test within that file and report back the results to the main process. We're going to repeat this process over and over again until our priority queue has been depleted, all of our tests has finished running. At this point in time, the main process would kill the workers, decide whether the testing suite had either passed or failed, and then it's going to show us the results in a user-friendly format. But how many workers do we actually need here? 1, 2, 100? It actually has a very significant importance on our benchmarks that we will see later. And the rule of thumb that most of the testing frameworks choose is that they are going to look at the number of cores on your machine, and they will use this number. So if you have, for example, 8 cores, you will get 7 workers, and the so-called last core will be reserved for the main process. Although in reality, it's really up to the operating system, but it gives us usually good results. But what you'd actually want to try to do is that you would want to play around with its number. So I took the same project that I've shown you earlier, and then I started using just different number when I start up my testing framework. Now, as you can see, when I used 4 workers, which is actually a lot less than the cores I had on my machine, I got the best performance. Now, when I used the parallelism defaults, I actually got 32 seconds, which is a lot better. Not to mention, when I started out, I already had 44 seconds. So I got a very sweet performance gain here, just from changing the slightest configuration. And the way it works is that you'd want to play around with the number of your workers to find the sweet spot, like I've just did. Now, after I went in another project where I work, and I thought, yeah, let's implement parallelism. It saves us a lot of time, right? It's very good. So this project is an HTTP API, and it has some very fast unit tests that run inside Mocha. And then I enabled parallelism, and I got these results. So as you can see here, when I've enabled parallelism, it actually took me a lot longer, almost double the time. So when I first got this, I started thinking, maybe something is misconfigured. Maybe it was just random, so I ran it a couple more times, and I still couldn't get it. So I started digging deeper and deeper to find out why this weird behavior is happening. And I found out the following. Creating new processes is not free. We need to allocate system resources, copy memory addresses, load modules. Depending on your process, maybe you have all sort of initialization. And doing that takes a lot of time. So what we've seen earlier, it's not that running the test took longer. In fact, it took shorter time, but the overhead of creating all of these workers were so long that using parallelism was just not worth it. Now, I want to drift to a completely different topic and start talking about implementing multi-threading inside our testing frameworks for performance gains. Now, in JavaScript in general, we usually tend to go through 2 approaches. The first one are the so-called promises or callbacks, where we would delegate our work to C++ threads from libuv or threads managed by our operating system. And the second approach would be to use worker threads, which is a relatively new API in Node.js that allows us to run multiple threads that can run JavaScript code. Now, like I've mentioned earlier, when we use multi-threading in our test, since a process can only handle a single test file at a time, multi-threading can only help us within a single test file because a thread is a property of a process. But I want to go back a little. Why did I start even talking about threads? Because we've just seen that in some cases, multiprocessing can behave very poorly. But let's not forget, there are some differences between the two. For example, creating new threads is a much more lightweight operation. Let's also not forget, we already get some threads by default when we start up Node.js, so why not use them? Also, threads can share stuff like memory and variables. We can also use that because acquiring them may require some time. Now, in the previous example that we've seen, it took us a lot of time to start up the workers, but if we use multi-threading instead, we can still improve the performance of our system by using parallelism. This time, not using multiprocessing, but using multi-threading. Now I want to start talking about more pitfalls and places where you start seeing some more weird behavior, whether parallelism would just not work or hurt your performance, or even create some nasty bugs. So in one of the cases, we have tests with I/O. And when I talk about I/O, I mean stuff like accessing a remote server or accessing a database or doing some actions against your local file systems. Now, in these scenarios, if you try to incorporate parallelism, you'd usually get pretty good results, but they also tend to somewhat get buggy because usually those operations tend to access some limited pool of resources. Now, what I mean by that is stuff like maybe sending requests to a server and then overloading it, causing it to crash, then your request to fail, or maybe when you start to initialize multiple processes. So if you try to listen on a port, for example, for an HTTP server, then if you get a port clash, then things might go wrong. And also, if you're connecting to a database, maybe usually database has some limitation on the number of connections. So if you would exceed it and try to make another connection request, it would probably be rejected and causing your process not to be initialized correctly. Now here I want to look at a more concrete example. Here we can see two tests, and these tests are in the same file, so we can only use multi-threading here. If we look carefully, the first test does some CPU-intensive task on the JavaScript main thread, and the second one does some I/O operation that just takes some time. Now, I also want you to assume that our framework only supports the promise approach here, and usually each framework will only support a single approach. And I think we can get a very good performance gain here if we would try to send out the I/O operation to run on the background using some maybe promise or callback, and then do the CPU-intensive task and keep our CPU busy. But let's see what would happen if we try to run this. So we'd first bump into the first test, where we'd start out this task, and our thread will be blocked. So we'd only be done with this line, and only by then we'd reach the second test, where we start up this I/O operation. So in reality, we don't have any parallelism here at all. Now, to tackle this issue, what we can do is that we can maybe flip the order between these tests, and that could help us because we can send the promise on the background, then we'd reach the first test until this promise resolved, we'll go back to it. But I don't really like this solution because I don't like the fact that the order which I write my test has such a big importance on the performance of the system. And usually, writing isolated tests is the best practice, so it kind of contradicts it. What I would want to do instead is maybe using a different framework that has support for worker threads, in which case it doesn't really matter if I block the JavaScript thread if I had several of them. Now, for this other example, I want you to picture that we have a database and some service that does some operations against it. For example, inserting or deleting a record. Now, we'd also have a test for each of those operations. On the insertion test, we would first insert a new record, see how many records do we have, and verify that we have one, the one we've just inserted. Now, on the before each statement, we'd clean up the database, so we're back to square one with 0 records. Then on the deletion test, we would first populate our database, then delete this record, see how many records do we have, and verify that we have none. If I run this in a serial manner, I think that it seems pretty okay, right? I think that if the insertion and the deletion operations work correctly or incorrectly, then the test should either pass or fail correspondingly. But what do you think would happen if I tried to run both of these in the same time? So I want you to picture this scenario. Let's say I'm running both of them. So when I start up, I'm inserting a record in both of these tests. So at this point in time, I should have 2 records. let's also assume that the first test finishes the operation first, so it starts the counting operation. At this point in time, it doesn't really matter if the second test is going to the next operation, because when I started the counting operation, I already had 2 documents in my database, and so I would expect to get 2 records at this point. And so when I get to my expect statement, I would expect 2 to be 1. Therefore, my test would fail, even though, when I write in a serial way, everything worked fine, and it did cover up my business logic here, and the toast seemed totally fine. But when I've introduced parallelism, I actually created a new bug here. So what you would actually want to do instead in parallelism is have more isolated tests, because it's the same principle we've seen earlier. We're accessing a limited pool of resources. This time, it's the database. This time, those records are clashing with each other. So what we can do instead is we could use unique identifier on these records, and then each operation for the database can operate against records with the specific unique identifier, because we probably wouldn't want to have several databases, because it usually takes some time to start it up. Now, after we've seen so many cases where things might go wrong, I want to give you a few rule of thumbs where you can really benefit parallel testing. So for starters, we have CPU-intensive tests. That can be either complex algorithms on large data sets, or even rendering UI components for front-end or full-stack developers, because rendering components is a rather CPU-intensive task. We've already seen also IO-bound tests where even though we have a lot of potential there, we need to be very careful in the way we write our tests and have them isolated from each other. Otherwise, it would create some nasty bugs. But I also think that it's very good, because writing isolated tests is actually a good practice. And lastly, we have very, very large test suites. Now, this is not something you're going to tackle every day, but I want you to take in mind that even if you save a small fraction of time here, usually these projects tend to have a lot of developers in them devoting a lot of time, so the impact may be very large. I want to start talking about frameworks, see which has support or doesn't have support for parallelism. What is the API? What is the default behavior? Because so far we've covered a lot of theory, but I know you guys probably want to get your hands dirty and actually implement some of this stuff. Well, for frameworks that have support, these are the popular ones that I've seen. We have Ava, Jest, and Mocha. And regarding those that don't, we have Cypress and Jasmine. As a side note, though, some of you may know that Cypress has some sort of support for parallelism, where it uses several nodes to separate the test file between these nodes, but it's a different topic than what we're talking today, and it's not going to help you on your local machine, so we're not going to cover this today. Now, for Jest, if you want multiprocessing, it's actually, you already get this by default when you start up Jest. But like we've seen when I started up, you'd usually really want to play around with the number of workers that you get, because it can have a lot of impact on your performance. Also, let's not forget, some people use Jest for very fast unit tests on the back end. And like we've seen in my previous example with Mocha, where it made things worse, if we'd actually tell Jest to disable parallelism, we can actually benefit from that too. So it's really worth trying to play around with this number. Now, for multi-threading with Jest, we have support for worker threads, where if you're used to calling the test function and then handing over the test description and then the test itself as a callback, then now we would instead call test.concurrent. What this would do is it would create a new worker thread for you and then run this test inside this thread. Now, for Mocha, if you want multiprocessing, it was actually introduced only in version 8 of it, so it's a rather new feature. And even then, Mocha is actually serial by default, so when you start it up, you have to give it the -- parallel flag, or either add some configuration to it to enable it. If you want to use multi-threading, then you'd actually need an external package here called mocha.parallel. Now, the way it works is if you're used to calling describe and then wrapping your test inside it, then now we would call parallel instead, which is a function exported by this package. It's really worth noting, though, that This package is actually only compatible with older versions of Mocha, and it's not even compatible with the version that supports multiprocessing. So we just have to choose between the two. Now, for Ava, we actually already have both support for multiprocessing and multithreading by default. What Ava does is that it creates a new worker for each test file that it finds, and also it uses the promise approach for multithreading. So whenever one of your tests returns a promise, you can move ahead to the next one. Now let's do a bit of recap on these frameworks and see some pros and cons. So for Jest, we did some multithreading and multiprocessing support. The problem with multithreading and test.concurrent with Jest is that it's not really documented well, and it can get a bit buggy, so it's kind of discouraged to actually use this feature. In Mocha, we actually have a lot of cons because Mocha wasn't designed in the first place to run tests in parallel. Actually, it was first designed to run very fast unit tests on the back end. And so only after it gained some popularity, then the community has started asking for this parallelism feature. And even then, in Mocha's documentation, it's actually discouraged to use it. So you'd probably want to use a different framework for that. Now, in Ava, we did support both multithreading, multiprocessing, but like I've mentioned earlier, Ava will create a new worker for each test file. Now, imagine if you have a lot of test files, so it can bring a lot of overhead. It can also create some bugs like we've seen. So what you'd probably want to do for the best performance is when you start up Ava, actually limit the number that it allows it to create new workers, and therefore it will help you avoid these nasty bugs. Okay, so to sum up what we've seen today, we started out by seeing why saving time on our tests is so important, and that is mostly because we just run them all the time. We've also seen how does multiprocessing works and multithreading in our different testing frameworks. We've seen how it's implemented, what different frameworks approaches do they take, what is the API, what is the default behavior, and we've seen some optimization tricks. That's it, everyone. Thank you.